Welcome to section 2.5, the Fundamental Theorem of Algebra, part 2. Part 2, we're just going to look at 4 examples of solving and finding all roots of the polynomial functions using different methods. The first example, f of x equals 2x to the fourth plus 9x squared plus 4. You can see off to the right here that I have graphed the polynomial. Just by looking at that, we don't know necessarily everything, but it doesn't look like it's going to cross the x-axis. So we got to think about, how else can we solve polynomials besides, finding some of the roots and using synthetic division? Well, in the beginning, we had talked about solving polynomials by factoring. So if you take a look at this, it's quadratic in form, and we are able to factor it. It'll be 2x squared, and then I'll have to have another x squared there. And so what I need to do is use my factors of 4 so that I can somehow add my middle terms to get 9x squared. And you can take a look here. This will give me a middle term of 8x squared plus 1x squared. And that's 9x squared. So now we can set our factors equal to 0 and solve each of these. So we have x squared subtract 1 divided by 2. And x squared is equal to negative 4. Take the square root of both sides, and we'll get x equals plus or minus the square root of negative 4, which is equal to plus or minus 2i. So that's why we didn't see those two solutions, because they are imaginary units. And then same thing's going to happen on the x squared equals negative 1/2, so it'd be x equals plus or minus the square root of negative 1 over 2. And so that would equal plus or minus the square root of 1 over the square root of 2i. And then if we simplify that just a little bit more, we will get x equals, rationalize the denominator, square root of 2 over 2i, plus or minus. So that gives us a total of 4 roots, which is what we're looking for. So x is equal to plus or minus the square root of 2 over 2i, and plus or minus 2i. And so that's why we weren't able to see them on the graphing calculator, is because all 4 roots were imaginary, had the imaginary unit in it. So therefore, it was not going to cross the x-axis, because only real roots do that. So there's example 1. On example 2, we have 4 terms. We potentially could look at factoring this using grouping, but you can find out pretty quickly that's not going to work. So we could also do our rational root theorem by finding some possibilities. But if you take a look at the graph, it does look like it intersects in one of the values nicely, which would be negative, or which would be positive 1. You can also see on the table that at x equals 1, the y value is 0. So at least this gives us a place to start. So we're going to start with x equals 1, use synthetic division. And so we have 12. If you have any missing terms, make sure you include those. In this one we don't. And so we carry down the 12. And forgot my negative there, but now that does add to 0, which is what we expect. So we've taken the cubic and broke it down to a quadratic. So technically we could solve this quadratic now by using probably the quadratic formula is what it's going to look like. But we could also look to see wherever it crosses, and you can see it crosses somewhere between 0 and negative 1. So what are we looking at there? Well, if we use, so right now either you could do one of two things. You could go ahead and take 12x squared plus 11x plus 2 and solve it. Or if you wanted to look at your rational roots, your possible rational roots, which would be factors of 1 and 2 over factors of 12. But the only ones I'm really interested in are the ones between 0 and negative 1. So I'm only going to list those. So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 6, 1 over 12, and then, let's see, 2 over 1, 2 over 2 is a repeat, 2 over 3, 2 over 4 is a repeat, 2 over 6 is a repeat, and 2 over 12 is a repeat. So those are the possibilities between 0 and 1. And so what you can see I did on my calculator is I plugged some of these values into the trace function, and I plugged in negative 2/3, and we can see that that one gave us a y value of 0. I also later on plugged in negative 0.25, which is negative 1/4, and also found 0. So if we want, we could keep going and use negative 2/3 as our another potential root here. So 12, 11, and 2, and we can continue to break down the polynomial. So 12 times negative 2/3, which would be negative 8. So 3 times negative 2/3 would be negative 2. And so we could do this again potentially with the negative 1/4, or now that we're left, we started with an x cubed, we broke it down to an x squared, and now we've taken the x squared and breaking it down to linear. So I'm going to stop here because this is an easy linear equation to solve. You get 12x, subtract the 3, divide by 12, and you will see my last root, which was negative 1/4, which is what we had up here as well. So you just have to remember, you have to show your work or justify what your solutions are. So x is equal to negative 2/3, negative 1/4, and 1. You can't just say I found them in the calculator. You can see how I've justified each of these when I've solved. So I use synthetic division on x equals 1. I use synthetic division again on x equals negative 2/3, and then I solved 12x plus 3 to get my last root. Or, as I said, you could have potentially solved this right here, the 12x squared plus 11x plus 2, and got the other two roots that way. Alright, on example 3, we have x to the 4th, so we have 4 roots that we're potentially looking for. We're looking at the graphing calculator window here, and we see it cross 4 times, so we know we're looking at 4 real zeros. One of them seems to cross nice at negative 1. You can also see on the table at negative 1 it does cross nice. Now, it looks like it goes and touches and then goes back. So when we talked about multiplicity, we know that an even multiplicity touches the x-axis but does not cross. So that means we can use it an even number of times. So let's go ahead and start with it with just the negative 1 once using synthetic division, and then we'll kind of go from there and see what it leads to. So we got this right here. We'll use synthetic division. And so as we go through this process, we should find out that the remainder is 0. That's what we expect to happen. But now we're only to an x cubed. If we don't understand multiplicity, we're not going to find the rest of the roots. So we have to know that, okay, we can potentially use this an even number of times. So let's go ahead and use it again. And so we're looking for another remainder of 0, which is what we get. Now it could potentially happen 4 times, but since the graph also crosses at 2 other places we can see, we know that that's all it is just 2. So now we are left with a quadratic. So we went from x to the 4th to x to the 3rd to x to the 2nd. So now we have x squared minus 10 is equal to 0, and we can go ahead and solve that by adding 10 to the other side and using the square root property and getting plus or minus the square root of 10, which that's close to 9, square root of 9, which is 3 something. So you can see each one of those is a little bit past 3 on the right and past 3 on the left with the negative. So we get x is equal to, we write all our roots down, negative 1. We only write it once, but we understand it has a multiplicity of 2. So we have a total of 4 roots there. Alright, in the last example here, once again, we're taking a look at this one. This one's a cubic. If we just plug it into the calculator, we do see that it crosses in between negative 1 and negative 2. So maybe we need to do our P over Q, our rational root theorem, to see what those potentials are. The thing is that once again, we need to look at this stuff and try to pay attention to what's going on before we just jump to using the graphing calculator. So one of the ways we can solve is solve by factoring, and this could potentially be a grouping problem. So if we factor out an x squared, that will leave us with 2x plus 3, and then if we factor out a 4, it'll leave us with 2x plus 3. So grouping will work in this instance because those binomials are the same, so we get 0 is equal to the 2 factors of x squared plus 4, and 2x plus 3, set our factors equal to 0 and solve. Now, as I kind of go through and finish solving this, we could have potentially used the graphing calculator to help us solve this problem. We do find out that it looks like 2 of our roots are imaginary, so that's why we only saw it cross one time, and then the other one is rational, and we get 2x is equal to negative 3, and x is equal to negative 3/2. So one of them was nice, and that was the one we could see crossing. So if we didn't use grouping, we potentially could have found the root negative 3/2, and you can see down here on the graphing calculator that I used the trace key and found out that at x equals negative 3/2, the y value was 0, and then we could have used synthetic division from there and got to the quadratic and solved it. But as I said, I think we need to make sure we're looking at all avenues and not just focusing on using the graphing calculator to always help in us solving. This is a polynomial, it's a cubic that's potentially pretty easy to solve if we notice that you can factor it by grouping. So those are the 4 examples I wanted to go through and just give you guys some different perspectives on different types of problems that you could potentially see on your test, whether it's factoring, quadratic and term, GCF, this one was a grouping, or knowing your multiplicity and understanding that as well. And also being able to do your rational root theorem so that you can tell when where the fractions are and where they cross as well if you need them.